Just when the ground in the North Pacific was supposed to be settling down, something strange started to happen. In the wake of the colossal magnitude 8.2 earthquake off Russia's Kamchatka Peninsula, the pattern of aftershocks began to break the rules. Instead of fading away, the seismic activity morphed into a relentless, chaotic barrage, a seismic swarm. Now hundreds of earthquakes are rattling the seafloor every day, and scientists at tsunami warning centers are watching with grave concern because this swarm has ignited a new and terrifying threat for 2025, the potential for an unexpected and powerful tsunami. So what exactly is a seismic swarm, and why is it so different from a normal earthquake sequence? Let's break it down. Think of a typical large earthquake like throwing a big boulder into a calm lake. You get one massive, violent splash, that's the main shock. This is followed by a series of smaller, predictable ripples that get weaker and less frequent over time. Those are the aftershocks. It's a pattern of decay. The energy is released, and the system calms down. A seismic swarm is completely different. Imagine that same lake, but instead of throwing a rock into it, you have a volcanic vent opening up on the bottom. There's no single big splash. Instead, you get a constant, chaotic bubbling. Hundreds or even thousands of pops and bursts of varying sizes, with no clear main event. The activity can rise and fall, and it can go on for weeks or even months without any sign of stopping. This isn't the story of a fault simply settling down after a big slip. This is the story of a system being actively disturbed from below. In a place like Kamchatka, which is essentially a giant volcanic arc, swarms are often caused by the movement of magma or superheated fluids deep within the Earth's crust pushing, stressing, and cracking the rock as it migrates. The recent megaquake may have fractured the deep plumbing of the region, opening up new pathways for this magmatic activity to surge. This is fascinating geology, but it begs the question, why is it a major tsunami threat? The answer lies in how tsunamis are born. Not all earthquakes are created equal in their ability to move the ocean. To generate a tsunami, you have to move a massive amount of water, and that almost always requires vertical displacement of the seafloor. Picture the bottom of a bathtub. If you just slide your hand horizontally along the bottom, not much happens to the water level. That's like a strike-slip fault, common in places like California. But if you suddenly thrust your fist upwards from the bottom of the tub, you lift the entire column of water above it, creating a huge bulge that collapses and sends waves racing outwards. That powerful vertical thrust is the signature of a subduction zone earthquake. Kamchatka sits on one of the world's most powerful subduction zones, where the Pacific plate dives deep beneath the North American plate. These zones are the planet's primary tsunami factories. The recent M8.2 quake was a massive rupture on this fault, unzipping hundreds of square miles of the seafloor. Now, the seismic swarm is hammering away at this same, already weakened area. The danger isn't necessarily that one of these smaller swarm quakes, say a magnitude 5 or 6, will generate a huge tsunami on its own. The threat is more complex, and it comes in two terrifying flavors. The first is what you could call death by 1,000 cuts, leading to an underwater landslide. The seafloor isn't flat. The continental shelf off the coast of Kamchatka is incredibly steep and piled high with unstable sediment. The main M8.2 earthquake acted like a sledgehammer, fracturing and weakening these submerged slopes. Now, the constant relentless shaking from the seismic swarm is like tapping on a cracked window over and over again. Each small quake could be the one that finally causes a massive section of the seafloor to collapse and slide into the abyss. This underwater landslide would act just like that fist in the bathtub, displacing an enormous volume of water and potentially triggering a tsunami that is far larger than what you'd expect from the earthquake in yes magnitude alone. The second danger is that the swarm isn't the main event, but a symptom of something bigger happening deeper down. The swarm could be the noisy expression of a silent, slow slip event occurring miles below, where the plates are moving without generating a sharp jolt. This slow, creeping movement could be transferring immense stress to a shallower, locked portion of the fault that didn't rupture in the main quake. The swarm is just a sign of the pressure building, loading this shallow segment until it's at the absolute breaking point, ready to fail in a massive tsunami-generating rupture. If this sounds like a theoretical horror story, it's not. We have a tragic, real-world precedent. The 2018 tsunami in Palu, Indonesia. A powerful magnitude 7.5 earthquake struck the island, but it was on a strike-slip fault, the kind that moves sideways and shouldn't generate a major tsunami. Warning centers were baffled. Yet minutes after the shaking, a devastating 20-foot wall of water surged into the city, causing immense destruction. What happened? Scientists now believe the intense, prolonged shaking from the earthquake triggered multiple massive underwater landslides along the steep slopes of the bay. It was the landslides, not the fault slip itself, that generated the deadly wave. Palu was a terrifying wake-up call for the entire world. It proved that the classic tsunami models were incomplete, and that we had to start accounting for these complex secondary landslide effects, the exact scenario now unfolding in Kamchatka. So, how do we watch for this threat? Fortunately, we aren't blind. Dotted across the Pacific Ocean is a network of incredible early warning devices called DART buoys. DART stands for Deep Ocean Assessment and Reporting of Tsunamis. Each station consists of two parts: a pressure recorder anchored to the seafloor and a companion buoy on the surface. The seafloor unit constantly measures the height of the water column above it with incredible precision. If a tsunami wave, which can be just a few inches high in the deep ocean, passes over it, the sensor detects the change in pressure. It then converts this data into an acoustic signal, sending it up to the surface buoy. The buoy transmits the information via satellite to warning centers in Hawaii and Alaska, where scientists can issue alerts in a matter of minutes. From Kamchatka, a tsunami would take several hours to reach the shores of Alaska and the U.S. West Coast, giving precious, life-saving time to act. In the end, the Kamchatka Swarm of 2025 is a stark reminder that our planet is a complex and dynamic system. The aftermath of a megaquake can be just as dangerous as the event itself, spawning new and unexpected hazards. We are witnessing a restless geological giant, and its constant rumbling is a sign of immense forces at play beneath the waves. The shaking is the symptom, but the silent, powerful response of the ocean is the threat we must now watch with utmost respect and attention.